Let's work an example of floating point multiplication. We'll be multiplying these two numbers, negative 0.3 in decimal by 500.25 in decimal. Now I've already done some work for you. I've converted each number to binary, then converted that to scientific notation, and then converted those numbers into floating point representation. Now you should be able to confirm all of these steps. Note that because 0.3 has an infinite repeating binary fraction, we had to do some rounding in the significand of the floating point representation. Also keep in mind that the bit patterns here are the biased exponents. So this value, which is 125, is minus 2 plus 127. Similarly, this value, which is 135, is 8 plus 127. Now going from here, we want to find out what x times y is. But we're going to need some bits and pieces. We want to get the significands and exponents separated out so that we can use the following formula to compute this result. We will multiply the significands and then multiply that by 2 raised to the addition of the exponents. So we need to know what these individual values are. Let's write them out. The exponent for x is simply minus 2. And the significand for x is 1 point followed by this sequence. So note that in this operation we will use the rounded floating point value and not the actual repeating value. So we will have 1 point, and then I will put in these specific bits here. And now I will compute the exponent and significand for y. So y's exponent is simply 8, and y's significand is a 1 point followed by this sequence. Now I'm going to leave out the trailing zeros because we don't need them. They're simply padding the right-hand side of this. So given these values, we can plug them into this and find out what the result is. Now, first, I'll just compute the new exponent, which would be 2 raised to the 8 plus minus 2, so 6. And that bit's easy. But this multiplication takes a bit of explanation. It will be computed as follows. I want to compute xs times ys. Well, this is this bit sequence, which I will write out. And I will leave off the last 0. We don't need it here. And I will also write out y significand here, so we're multiplying by that. I'll start from this edge so I can align them. And now, to multiply these two numbers, I proceed as I would with normal multiplication, which we haven't done with binary numbers yet, so let's see how it works. 1 times this whole number means that I put that whole number on this line here, which I'll do. Now then I would do 0 times that whole number and put it here in this position 1 column over. Of course, 0 times this whole number will be 0, so let's just skip that and leave it out. And then 0 again, well, that moves us over another column, and then 0 moves us over another column. And so it isn't until I get to this 1 that I then copy this whole number again and put it here, which I'll now write out. And now I have another 0, so that pushes me over another column that I can ignore. And then I have this 1 multiplying the whole thing. And actually I have 1, 2, 3, 4, 5 ones in a row. So I'm going to put 5 copies of this number, each shifted over by 1 position. Having written all of these copies of the first value out, I now add them all up to get the final result. Let's add up all of these values. So the first few columns are easy. You only have here 1, 0, and then 2 1s. And then here we start actually adding different numbers together. So we have a 1, 0. Now 1, 2, 3. Well, 3 in binary is 1, 1, so there's a 1 here, and then a 1 up there. 1, 2, 3, 4. This is interesting. 4 in binary is 1, 0, 0. So that means we have a 0 here, and then a 0 carries over into the next column, and then a 1 carries 2 columns over. So now, adding up this column, we have 1 plus 1 is 2. That is 0 and yet another 1 in this column. So we're adding 1, 2, 3, 4, 5. 5 in binary is 1, 0, 1. So that last one goes here. The 0 adds nothing, but then 2 columns over we have a 1. So this is how larger numbers carry in binary. Here we add 1, 2, 3, 4, 5. So 1, 0, and then a 1 in the column over. So this is the result of the addition. And now we need to find out where the binary point goes here. And we can do that by counting up the number of positions after the point appear in this number, and the number of positions after the point that appear in this number. There are 32 bits after these 2 binary points in total. And so, starting from the right here, our binary point will be 32 positions over. This position here is 32 bits over from the right. And so that is where this binary point goes. However, this is the result of multiplying our 2 significands. So this result in the end is further multiplied by 2 raised to the 6. Although this will equal our answer, we have to normalize it. Recall that for floating point representation, we always normalize the result. That means that this binary point has to move over 1 more position so that this 2 to the 6 will become 2 to the 7. Now, given this number, we can figure out the final floating point representation. Our first bit will be a 1 for negative because we are multiplying negative 0.3 by positive 500.25. So a negative times a positive is a negative, therefore a 1 goes here. The next 8 bits are the biased exponent. So we take our actual exponent, add 127 to it to get 134. So here we need the biased exponent, and it will be 1 0 0 0 0 1 1 0. That's 134 in binary. And then the remaining bits that go here are the leading 23 bits of this sequence of bits, rounded up if necessary. So to find out which bits go in here, we need to start from this position and count 23 bits over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. That means that we will only have bits to the left of this line, but because there is a 1 here, we have to round up. So this 1 becomes a 0, carry the 1 again, that becomes a 0, carry 1 again, put a 1 in this position. So these 23 bits will go here, starting from this position. So this sequence of bits is the floating point representation for our multiplication, and if we convert this back into decimal, we will actually get negative 150.07501. So this little bit of rounding error here was introduced. The actual result would not have these last 2 decimal positions.